easier than fluid flow, mainly because this energy equation in this form is linear, provided you know velocity. Okay. If you are given u, then it is a linear equation in temperature. And then this book by Kreyszig comes into picture. Okay. You can use one of the many methods they have given, the book has given, for solving this problem. So, this left hand side in momentum equation is mass times acceleration, which is the material derivative of velocity. So, what is it? This du dt is acceleration. In the energy equation, the left hand side can be written as rho c times the total derivative. It is the material derivative of temperature. If you recall our discussions, so that is why I keep saying do not forget the global part of it, because we have discussed a material derivative and we were talking about a particle carrying information in the form of either momentum or energy. So, this term, like acceleration, it is the temperature content, which is internal energy being carried by rho c I times temperature will give you, well, actually I plus p over rho, as we had discussed, which is internal energy plus p over rho, which is enthalpy being carried by the flow. So, it is thermal signature being carried by the flow, okay, like acceleration. So, there is an analogy between the two, except that acceleration is a non-linear term, this is a linear term. So, instead of acceleration, the technical term used is advection. Some people also use the word convection, but advection is a technically correct term for energy being transported in a flow field. Of course, if u is 0, there is no advection. Then what are you left with? You are left only with the right hand side. So, you recall that this term mu del square u, we had called it the viscous term. You may also call mu del square u the viscous stresses. So, similarly, k del square T is called the diffusion term. And because it is multiplied by thermal conductivity, it is also called the conduction term. So, the energy equation that is written here is called the advection diffusion equation. Okay. You have the same form for momentum also, okay. Except that mathematically it is more complicated. Now, we have a gradient of p here in momentum. Now, you could have an equivalent term for the energy equation also if you had heat generation. If you had heat generation, then you would have written q dot equal to integral over C s q dot n d s plus integral over C v q dot generation d v, with the sign convention that heat generation. What is heat generation? You may have, let us say, chemical reactions taking place inside the region. So, familiar example is I think in okay, now Frank White does not have heat transfer per se, but Frank White has another book on heat transfer. Rather than getting into a new book, I will send you some model problems to work on related to heat transfer. Okay? But I am trying to keep the discussion as simple as possible, and I am relating to fluid flow all the time. So, Q generation is, it could be due to, let us say, setting of the cement. Okay, you have applied cement and it is drying up, its temperature goes up because of chemical reactions happening inside. There could be other factors also. There could be combustion taking place, which is a kind of a chemical reaction leading to this generation term. Similarly, the reaction can be exothermic, endothermic, that will change the sign of this Q gen. So, in that case, the energy equation will be rewritten so this Q gen will have units of watts per meter cube. So, it is a slightly revised form of the energy equation. Okay, so, when you write it in this form, then there is a similarity between the momentum equation and the energy equation. Now, the local version of mass, momentum and energy equations require specification of the material medium. So, we had a constitutive relationship. The specific form of these, the local forms of the physical laws stem from a constitutive relationship. We have worked with a Newtonian fluid and we related it was a linear stress strain rate relationship. Okay. Now, for energy equation, hey, did I say Kirchhoff's law last time? Should be Fourier's law. I mean, this Q equal to minus K gradient of T is, I do not know why I was thinking of Kirchhoff's. Please write it as Fourier's law of heat conduction. That we wrote as minus K gradient of T in vector form, or in index notation it is minus K I equal to 1, 2 and 3. For 3 dimensions it is 1, 2, 3. Okay. It is a Fourier's law, please make that correction. So, this is what led to del dot Q became minus K del square T. That term came from Fourier's law of heat conduction. So, if your fluid medium like blood is not Newtonian, we call it non-Newtonian. Similarly, if materials in which Q is equal to minus K gradient of T is not satisfied are called non-Fourier media. But for the commonly encountered materials, Fourier's law of heat conduction is known to prevail in the sense that thermal conductivity can be well defined. Okay, so, if you look at handbooks, they will give you thermal conductivity values everything from mild steel to copper to air to liquid water to oils, all of them have a well defined thermal conductivity, which means Fourier's law of heat conduction is applicable. Now, we were closely relating the Newtonian fluid model to the parallel plate experiment. This was the parallel plate experiment, in which a force F gives rise to a velocity u. So, if you do see, I was referring to non-equilibrium thermodynamics. Can you name one scientist or engineer who is associated with equilibrium thermodynamics? Give me one name, just one name from thermodynamics. Carnot. Some people say Carnot. I don't know if it is Carnot. I was told Carnot, so I am just repeating it. Yes. So, for equilibrium thermodynamics, for non-equilibrium thermodynamics, the discussion starts with a less familiar name, Onsager. Okay. So, Onsager showed that the entropy generation rate, which should be positive for a non-equilibrium. So, this what is non-equilibrium thermodynamics? Is a situation where you apply a force and you get a flux. Okay, it is like applying voltage, getting current. It is exactly the same analogy. And then what is voltage times current? In the resistor, what will it give rise to? Joule heating. It gets dissipated, that means it has become useless. Well, not completely useless. If you are going to use it for warming up the room, then it is useful. But let us say compared to the original resource, it has become practically useless. Voltage times current is Joule heating. Okay. The voltage is force, current is flux. So, Onsager showed that force times flux will be the entropy generation rate. So, this voltage applied across a resistor is not going to cool the resistor, it is only going to heat it. So, voltage times current is, if you think in terms of Joule heating, it is positive. So, that is the entropy generation rate. So, Onsager showed that force times flux is the entropy generation rate, which is positive. So, in this course we have not really gone deep into second law of thermodynamics, but I am just stating it for completeness, because we wrote q dot less than 0 for the global formulation under isothermal conditions. So, in this parallel plate experiment, what is force? It is F. What is the flux? It is velocity. Okay. You applied force and now the plate is moving. Of course, you can also set the plate in motion with some velocity u, but that will require a force F. Okay. And that force depends on the fluid properties, the fluid that is present in the gap between the two surfaces. So, force times flux will be F times u. So, in this context, F times u, but what is F? It is mu area u over h times u, right. Mu u over h is the shear stress times area times u, which is greater than 0, but u square is positive, h is positive, area is positive, which means mu is positive. Okay. So, the result, Navier-Stokes equations will give you respectable or realistic answers only if mu is positive. Okay, so, actually mu equal to 0, then there is a question mark, but quickly we corrected it with boundary layer theory. Now, going back to heat transfer, so this is what is this is Newton's parallel plate experiment. It's also in it's also Couette flow. So, a model problem that we think of in heat transfer is slab. So, this is a slab of some finite thickness L, and you apply a temperature difference across this slab, and then Fourier's law Q tells you that Q will be equal to K T1 minus T2 over L, and the entropy generation. So, what is the, well, here the forcing function is temperature difference. Okay. So, in fluid flow it is, you can think of force or pressure or shear stress. So, stresses are the forces. Here temperature plays the role of forces. Okay. Temperature difference. Okay. And the flux is the heat flux, the energy transported through the slab, and force times flux will be K T1 minus T2 square divided by L, which is greater than 0. So, K greater than 0. So, the energy equation is realistic only for K greater than 0. Okay. These are the constraints imposed by second law of thermodynamics. Okay, now let us focus on the solution of the energy equation. So, I remembered there is some confusion about tomorrow. I checked with the authorities. They have confirmed that Saturday will not operate like a Friday. We are free to use Friday by scheduling classes in advance. This quiz was scheduled more than a month ago, if you remember. So, there is a quiz 8:15 to 8:45 tomorrow. If somebody else has booked a class in the same slot, you please request that person to shift it. Okay? There is a quiz tomorrow. Tomorrow is not a Friday. I think there is some confusion, and we may get a clarification today, but I have been told quite directly that tomorrow is available for makeup, but it is not a Friday. Okay. And the syllabus for tomorrow would be fully developed flow and potential theory. Okay. So, that means one question on fully developed flow, one question on potential theory. You do not need, you will not require any handbook, I mean handout, not handbook, handout. Whatever is required will be given to you in the question paper. Okay. And tomorrow's quiz will have to be solved using a separate answer sheet, not on the quiz question paper itself. Okay. Make sure you have a separate answer sheet for it. So, this equation is now in coordinate free form. Suppose you want to solve in Cartesian coordinates, then you have to express, so which in our shorthand notation is u t x plus v t y. So, if you refer to our notes, you will see that a suffix has been used for partial differentiation. If you want to use a suffix for indicating a velocity component, if you want to use an extra symbol for velocity component, use it as a superscript. Okay. So, u superscript r will be velocity in the radial direction, but do not use it as a suffix. So, suffix is reserved for partial differentiation. So, here u t x v t y, t x is this partial derivative. Similarly, del square t will be t x x plus t y y plus t z z if it is 3D. So, this is the 2D form. Okay. And q generation, this will be a prescribed quantity. Okay. So, now this is a second order partial differential equation. So, you will require initial and boundary conditions. Like in a flow field, the initial condition could be that the fluid is at rest and suddenly you applied, let us say, a pressure difference, or you started moving a surface. The disturbance is initiated at time t equal to 0. So, initially the medium is at rest. So, velocity is 0. Okay. If it is a very large fluid space, then pressure would be hydrostatic. If it is a small space, you can assume pressure to be constant. So, similarly, in the heat transfer setting, you could write T equal to maybe T c, let us say, which is called some reference value. Usually ambient. So, you can ask, this room does not have air conditioning. Suddenly at time t equal to 0, you turn the AC on, and then you will have cold air flooding this room, and slowly wherever you are, you will start feeling its effect. Can you solve that problem? What is the problem? You want to find temperature at this point, the AC duct. Where is the AC duct here? Maybe these are the ducts. Probably those are the ducts. Cold air coming in, and I want to find out how temperature at this point decreases with time and reaches steady state. Can this problem be solved by working with this equation? Is this the equation for solving that problem? Yes. Okay. That is the kind of problem you can solve. Okay. Now, you can do that in a tube. You have flow in a tube and you are heating the tube. So, the fluid inside is getting warmed up, okay, both at a point as well as along. Solve this equation, it will tell you for a given heating rate how quickly the fluid will heat up, okay, or how slowly it is going to get heated up. So, whether it is a tube or a parallel plate or a room or the atmosphere, it's the same equation, same energy equation. So, but then you have to start the calculation. It starts with a cold state. That means, let us say this room is at room temperature and then AC comes in, AC air comes in, so, and then the temperature goes down. In addition, you will need boundary conditions. Now, in a typical problem that we have studied in this course, you have a surface and flow going over the surface. So, this fluid may be cold and this wall may be heated. Okay. So, the wall is at some temperature, maybe 55 degrees Celsius, okay, and then you have air going over it or water going over it, but air or the fluid is getting heated up, but when it comes in it has an inlet temperature. So, at x equal to 0, that is the inflow plane, T is equal to T c in the fluid medium, as it goes over the surface, the lower wall, which is y equal to 0, temperature is equal to some wall temperature. So, when temperature is given, that surface is said to be isothermal. So, one kind of boundary condition is the isothermal condition, T prescribed. The second type of boundary condition is when heat flux is prescribed. Heat flux is Q, but now we are talking about the wall heat flux, which is Q wall, which is minus K Q was equal to minus K gradient of T. Okay. So, gradient of T evaluated in the normal direction. Okay. So, Q is equal to minus K gradient of T, or when you talk about the heat flux being pushed into the fluid, that would be normal to the surface. So, that would be minus K times the derivative of temperature with the normal coordinate, which is y in this case. This is another type of. So, you are really prescribing this is a derivative of temperature at the wall. So, this is the second type of boundary condition where the wall heat flux is given. So, for example, you may have a flame, you have a hot surface, below you have a maybe a candle flame or a fire. If it is a furnace of a thermal power plant, you will have hot gases inside, you will have coal or methane or oil burning. So, that will impose a heat flux boundary condition on the wall. Okay. Now, what is K? K is thermal conductivity of what? In this problem, we are talking about temperature distribution in the fluid medium. So, this K is the thermal conductivity of the fluid medium above the plate. So, this Q wall is coming from this side and K is of that side. But sometimes we focus on the wall, then of course, K becomes conductivity of the wall. So, you have to be aware of what calculation is in progress. So, I may write here Kf. Okay. So, this material has a conductivity Kf, viscosity mu. Okay. Why do you need viscosity? Because you have to solve the mass and momentum equations. That velocity goes into solving the energy equation. Now, in some problems the wall heat flux is 0. What is that condition called? Somebody said, I am not able to hear it. Somebody said adiabatic, I think, which is correct. If the heat flux is 0, adiabatic or insulated, these are conventional terms used in the subject of heat transfer. The surface is said to be insulated if heat flux is 0, in which case this derivative is 0. Okay. If heat flux is 0, this normal derivative is 0. That is called an insulated condition. So, the third possibility is it is insulated. Okay. So, that means, okay, if the surface is insulated, then you are doing nothing to the fluid thermally speaking. So, what it means is not all surfaces can be insulated. You may have cold air coming in, but this wall may be treated as an insulating wall, because you want all the cold air to remain inside. Okay. So, there is no, these are passive thermally speaking, these walls, and all the cold air is coming in. Okay. So, not all surfaces are insulated, some of them are. There is a third possibility which is called a convective boundary condition. So, consider this problem. This is a solid medium and then you have a fluid medium here above. Okay. And so, there is flow and then there is a solid medium, and you have heat transfer taking place both in the solid medium as well as the fluid medium. What is the goal of the analysis? What is the goal of the analysis in Navier-Stokes? To find velocity and pressure, then put them in the constitutive relationship and get stresses, integrate stresses and find forces and moments. That is the Navier-Stokes approach. In energy equation, what is the approach? Solve for temperature from the energy equation, plug in temperature in the constitutive relationship, which is now Fourier's law. Okay. Then integrate Q over the surface as appropriate and get the energy transfer rate. Okay. Temperature itself may be of interest, but you may also be interested in the total energy transferred from the material to the surroundings. Okay. So, in a say this is the problem where you have a fluid medium and you have the solid medium. So, what are the equations you will solve here? Mass, momentum and energy, which is rho c and let us say q gen is 0. So, these are the equations you will solve in the fluid phase. What are the equations you will solve in the solid phase? Well, what is velocity in the solid phase? 0. So, you do not have to solve for the mass and momentum equations in the solid phase. Okay. And in the energy equation, the entire left hand side. So, that there was u dot gradient of T, that term is 0. So, in the solid material you are only solving k del square T. This is the equation being solved. Now, you have to watch out, because this rho c here is of the fluid phase k f, and this rho c here in the solid material is of the solid phase. Okay. Now, this is very much like the two fluid problem we had studied, and then there was an interface. We had the momentum equation in one fluid, momentum equation again in the second fluid. Here we have applied energy equation in one medium, energy equation again in the other medium. You can have solid and solid, solid and fluid and fluid, all possibilities are there. And then you have an demarcating interface. So, you solve these equations individually and then you have to blend them at the interface. So, there are interface conditions. What are the interface conditions? The interface conditions are like in one fluid on top of another fluid, both of them are moving. And then we said the no slip condition will hold. That means velocity as you calculate from one side will be equal to the velocity as you calculate from the other side. Velocity is continuous. Okay. Similarly, the shear stresses are continuous. Okay. So, extending that idea to heat transfer, you will have continuity of temperature and the continuity of heat flux. These are continuous across the interface. Interface conditions. So, let us say y equal to 0. Suppose you are solving on the fluid side, which is y is equal to 0 plus. Then you will say T f is equal to T s. And if you are solving on the solid side, this is at y equal to 0. So, continuity of heat flux, continuity of temperature. These conditions have to be applied at the interface, and then you have your own energy equations in each of the media. So, this will have to be solved in general. So, when the problem becomes very difficult, we opt for certain simplifications. One simplification that is very commonly used in engineering is the use of handbooks. Okay. So, engineers tend to generate knowledge and codify them in the form of handbooks. So, one such handbook approach particularly when you are solving for the solid phase. Okay. So, between the two, solid and the fluid part of the governing equations is harder. So, suppose you are interested only in the solid part and you are willing to approximate the effect of fluid motion, then the handbooks carry information on a quantity called the heat transfer coefficient. And is given a symbol H. Okay. So, it is the use of a heat transfer coefficient will simplify calculations. First of all, it decouples the solid and the fluid phases. H will contain information about the influence of fluid motion on heat transfer. How exactly does it work? So, that we will see on Monday.